Thanks, Melissa. Day 5, right? So if I understand the program, you started off with more physical stuff, and you're actually getting to more the communication end of the meeting and the outcomes. And so my second talk will actually move into that communication and why we're in the business of climate change. And my first talk here will really kind of get you to think about how do we really assess and evaluate the observations we have, and how do we actually connect them to anything to do with humans. And I'll put a particular emphasis here on stuff from the oceans, typically because I'm an oceanographer actually, and so oceanographers tend to think about the oceans, but actually all of this is applicable to any of the work that you might do in the upper stratosphere, the middle troposphere, the surface of the Earth, or the surface of the ocean, or the deep interior. Detection and attribution is really a method for evaluating models and observations. The detection part is actually about thinking how you detect change that's statistically significant and bigger than the noise signal. Attribution is really about actually making a connection between the various, in the case of climate change, the various drivers in the climate system, whether it's, and I'll come back to this as I progress through the slides, the various drivers in the climate system, and attribute those as the cause of the observed changes, or a combination of those things as the observed changes. In its narrow sense, you might think that attribution and detection is just a statistical process. And for some parts of the detection and attribution community, that would actually be completely correct. But actually, it's a lot about drawing together the physics of how the oceans or atmosphere work, how the climate system works, with other evidence to come to conclusions about the influence of, in this case, humans, but it can be the influence of other things in the climate system. So all of you have probably seen this slide. Who hasn't seen this slide, by the way? Has anyone not seen this slide? Fantastic. This slide is really a summary of all the observations that came out of the last IPCC report in 2013. And really what it's drawing together is the fact that the Earth system has changed. So, if I just run through each of the individual panels here, this is the Arctic summer sea ice extent, and if you look at that, it's been this is the observations of Arctic sea ice extent from all of the available sorts of observations that exist. So this is 1900 is pre-satellite era through to the present, which includes the satellite era. And what you can see is actually a compilation of all these observations of sea ice extent over the last century shows an inexorable decline in the Arctic sea ice extent, and there's other evidence around the Arctic sea ice extent as well. But it shows basically we've come to a minimum and it's continuing to decline. So that's just an observation that's been gathered from all sorts of observation records, including just historical narratives. Then there's this other kind of observation, which is the total ocean heat content for the whole of the Earth. So this is really a compilation of all of the observations of temperature from whatever typically down to 700 metres for this particular curve. And what it really shows is that actually in the 1950s we started to make measurements of deep ocean temperatures down to 700 metres, just down to 400 metres in the early part of the 1950s systematically, and then progressively that we've got more and more observations. The Argyle ray kicked in, and you can see actually the uncertainty in this global estimate is actually decreasing progressively through time as the observation system gets progressively better and better. And one of the key results of the sixth assessment was actually that in creating this curve, the total energy here, which is in joules, the total energy change stored in the oceans is actually about 90% of the energy stored in every component, right? So the atmosphere holds no energy, basically. The conversion of the ice sheets and glaciers to free water isn't that much energy. And the uptake by the solid earth, by the ground, is a significant component. It runs at about 3% or so. But actually, the oceans are the key to the storage and energy. And John Church talked to you guys about that on Wednesday, I think. So, but the key element here is that the energy balance in the Earth is dominated by the oceans. But perhaps from the point of view of today's conversation, this is a rising heat content, and it's been sort of inexorable on a global scale. Sea level's going up, and what you can see here is that the sea level rise actually has a slightly different character to some of the other curves. It's almost linear. There's a very slight curvature in this curve, which has been talked about in the literature. And in the last decade, sea level was running at 3 to 4 millimetres a year, and with about 70% contributed by thermal expansion, 20% by that 70% composed of thermal expansion, which is about 50%, the other 20% by glaciers, and another 25% roughly through contributions from Antarctica and Greenland. The new contributions from Antarctica and Greenland are really new in our understanding of the observations, and that leaves some key questions which I'll actually talk about later on in this talk. So, you know, with rise, I haven't put in the most obvious graph, which is actually the rising atmospheric CO2, but through wind action and mixing, you get a rise in the partial pressure of carbon dioxide in the surface ocean. And there are about 4 stations in the world that actually have been recording this in the observations, but they show that it's a very similar kind of rise. There is some extra noise in here. We can talk about that too, but as a consequence, we've got an increase in ocean acidity, so a decline in pH. And if you calculate the change in the number of hydrogen atoms, it's about 30% since pre-industrial, since the 1850s, since pre-industrial times. And then there's this curve here, which is a little bit different to the ones that you might have been thinking about, which is actually about the ocean salinity. Ocean salinity is, in some ways, some of the best evidence we have for the changing nature of rainfall over the Earth's surface. For those who don't think about the oceans, if a region that increases in salinity, if it's on the right spatial scale and with the right temporal scale, actually is basically reflecting an increase in evaporation or an increase in P minus E, so a net water loss from the surface of the ocean. And the areas that are getting wetter, like the equatorial zone and the high latitudes, they are reflecting actually an increase in precipitation over evaporation. And what this curve is actually an index between the areas that are salty and the areas that are actually fresh. And observations of surface salinity aren't reliable prior to the 1960s, but what you can see is from the 1970s through to the present, this index of the salinity difference between high and low salinity areas is actually going up as well. And this is kind of a summary, if you like, at the global scale of the observed temperature change. So as a consequence, IPCC in the fifth assessment report took all these sort of lines of evidence, and we do rely on multiple lines of evidence, no single line of evidence to support the conclusion that the observation was showing that the climate system has changed. And so we were able to conclude with this very famous sentence, actually: warming in the climate system's unequivocal. And if someone can remember to ask me how we actually came to that phrase, I'll tell you about it in the next half of the talk. Okay, so it's all very well to say observe this climate system's warmed up. It's all very well to say that, but actually how do we know what the cause and contributions, whether it's natural or human? And so that's actually the heart of the question around attribution and detection, right? So we've detected it relative to our understanding of noise that the climate system has changed. We're able to make this statement, but we actually haven't connected it to anything to do with human activities, right? So the second half of the challenge is not to know that the Earth has changed, but actually to figure out whether we can attribute or connect it to some sorts of causal relationship, whether it's human activities or others. So the sort of questions you might ask yourself in the attribution and detection space is something like, well, are those observed changes anything to do with human activities, or is it completely natural, right? That is actually the first question we might ask. That's more or less a detection question. You might say, well, actually, what are the scientific explanations of the observed changes? So this is thinking about establishing the connection between the observations and the models. Actually, most of my colleagues don't do either of these things very well at all, right? Most of my colleagues don't. And why don't they do that? Why don't they actually engage in this sort of activity? And part of the reason is actually not interested in human activities. What they're really interested in is the variations, PDO, ENSO, all those sorts of things. And a lot of those don't show any indication of climate-driven or human activity, and so it's not actually an area of interest for them. But actually for answering the question around whether humans have caused climate change, it's absolutely essential, right? If you don't answer that question, then actually we can't mitigate for climate change because you haven't got past the first base. So the question is around the human activities is actually important, and it's important to do it in a very credible way. Now, there's another kind of question that happens actually, which is sort of often how other kinds of people are involved in the conversation around climate change. There's perhaps skeptics. I don't quite like the word skeptics here, but so they can say very legitimately, can we account for the observed changes just from the natural internal variability in the climate system? And you know, that's the person who's trying to say, well, I can understand the changes. Geologists often fit into this category, actually. And there's some classic examples from history. Arrhenius in the 1890s was actually thinking about the rising surface temperature of the Earth. He had a theory at the time, right? It was based on CO2 in the atmosphere, and it was just fine. But then just shortly in the mid-1890s, the temperature went down, of course, and he was kind of forgotten about because the Earth temperature was actually going down. It turns out, of course, we were just looking at some aspects of variability at that time. And so it's really important, actually, to kind of determine whether it's natural or unnatural, i.e. it's driven by humans. So what is the attribution process? So what is the challenge that's actually in front of you to think about in the story of attributing? We have, now this is a figure out of the fourth assessment, but it just illustrates the time history of the global average temperature, and you can see it's rising. And that's all very interesting. The state of the system has changed, that's clear. Okay, but actually, what are the possible drivers? Let's think about the possible drivers of that rising temperature curve. Everyone will say greenhouse gases, but actually it's a little bit more complicated than that, and I'll illustrate that in a moment. But for the moment, let's just think about greenhouse gases. Greenhouse gases, right, and here this is a diagram of how greenhouse gases have been relatively stable for the last 10,000 years, and they're shooting upwards in the modern Keeling record since the red part is since the 1950s. Okay, so greenhouse gases is one obvious candidate, but actually there's some other competing ideas that we'd also like to exclude, right? We'd like to exclude the competing ideas. How are you doing? Good. So the competing ideas are from aerosols. Actually, there's some other natural ones, the volcanic eruptions, for instance. So volcanic eruptions, they actually contribute. Well, actually, in the literature and from other parts of the community, this is an item that is discussed, and it's actually one of the first things that has been recognised as driving the planet. there's also some obvious things like solar variability on the planet. We all understand that there are sunspots on the surface of the ocean, surface of the sun, and on the surface of the sun, those solar flares and black spots actually vary on a 11-year period the sun's radiation. So that's actually another plausible driver in the system, and then there's just simply the internal variability. So the question at heart is, at least from this list, is actually, is this observation explained by these different hypotheses here? Is it just any single one of those, or is it actually the combination of them, or is it actually none of them? Right? None of them would be where you actually didn't get any right ideas, and so you would like to know whether you can reject them. So the challenge then really is that we've got all these drivers. We've got a set of, this is why you've got me on the last day, by the way, right? You've had all the fluid dynamics, you've had all the physics, you've had all the radiation, you've thought about the energy balance, but now actually what we want to do is we want to use the models, the articulation, the theory, and how they ameliorate or modify the drivers of the climate system and express it on the surface of the Earth. And that expression on the surface of the Earth is actually what you want to compare with the observations, right? So the models are an intrinsic part of thinking about how these changes in the surface temperature of the Earth have actually changed, right? And so the challenge in the attribution is really to figure out the contributions of these various drivers in the climate system expressed through the theory of the climate system, and whether that pattern that we get on the surface of the Earth actually looks like this pattern in some way that we can assess statistically. Okay, so that's the challenge that we have. So let's just think a little bit about total radiative forcing. Now, really I'm just exploring the different range of hypotheses that are sitting here that are driving the climate system. Okay, so normally we think greenhouse gases is everything. Well, that's kind of true. Here they are lumped up in the last assessment from AR5. And you can see that greenhouse gases are the biggest contributor, actually, out of the others. There's other anthropogenic, and then there's, I've forgotten, I can't even read what that says. And then there's some various indirect drivers, and then the total radiative forcing. But what you can see is actually the carbon dioxide, whilst it's the biggest, there are a few other drivers here, from methane, what else is there? Water, and then there's the CFCs, hydrochlorofluorocarbons, the ozone, the nitrous oxides. And then over here, actually in the aerosols area, we've actually got some huge negative drivers, right? So if you look at this, the aerosols are actually cooling the planet. It's an unfortunate aspect of our current experiment on Earth, is that we're driving two experiments at once at least, right? We've got the greenhouse gases going in, and actually we're putting out lots of radiative pollution into the atmosphere, and as a consequence, altering the radiative properties of the Earth by increasing the reflection out to space. So we've got a very, you're doing the super problems today, right? Really, you should have done the problem where you just drove the Earth with CO2 and drove the Earth with the aerosols and thought about that as distinct from the mixed problem, which we're conducting on Earth, which has got the aerosols here as a negative. And interestingly, if you look at these other greenhouse gases, they're actually as big a contribution as the aerosols themselves. So it turns out that CO2 is probably the biggest driver when you look at it that way. Okay? So the first and most important thing is actually the radiative balance is out of equilibrium, right? You'd be worried if that turned out to be a negative sum. It does turn out that all of the human factors, which is what's on this graph, is basically still positive because the aerosol contribution hasn't overwhelmed our observations and understanding of radiative balance. So that's the first part. So that's good. But the second part is actually, and it's really important to understand that the drivers of the climate system aren't just a an average sum, right? I've shown in the last figure that it's an average sum of big changes since the 1960s, since 1950, since in 2011, 1980s. You can see that gives you a kind of a mixed view of the world. But actually, the drivers of the climate system have a huge temporal variability. And here's a classic, the volcanic eruptions that have come. So this would be Pinatubo. It's a huge cooling of the planet. But it's got a very short time period, right? And you can exploit the time period, the temporal characteristics for actually separating out the drivers in the climate system. Here you can see solar variability, right? Something that's often been proposed by the skeptical community as a possible driver of the climate system. And here you can see the 11-year cycle, but you can see that in our measurements out from observations and models actually, in our measurements that the solar variability is not trivial, but it's actually not all that large in total radiative forcing terms. You can see that all the greenhouse gases do turn out to be positive. The net effect, though, temporarily, is that with the punctuation from volcanic eruptions, that it does actually become negative at various times. For those who are old enough to remember Pinatubo, there were beautiful sunsets actually that came as a direct consequence of that volcanic eruption that actually kept on for another couple of years. In fact, in the Hank Stoll, who wrote about the year that actually there was no summer, that was back in the 1850s and the 1812 Krakatoa explosions, right? So this connection to the volcanic eruptions driving the climate system is actually well known. Okay, so let's think about how to do this in a way that's quantitative and scientifically convincing, as distinct from what Matt will talk about, which is actually being convincing in a communication sense. So the key thing is to actually try and exploit the temporal characteristics and the spatial characteristics of the forcings so that we can kind of separate out the various hypotheses. So back in the third assessment report, we actually started doing this sort of stuff. So this is a figure from Andrew Weaver and Francis Spears. Here's the observations, and you can see that in this instance they're being filtered up into a kind of a 10-year pattern. So you've got a time history here of the evolving state of the surface of the Earth. And then you would have a comparable model simulation. In this case, just imagine this is all forcings. So it's got all of the forcings in it. So what we're thinking about here in this particular, what we're showing in this particular schematic might be just thinking about a detection problem. How do we explain the observations, the observed changes on the surface of the Earth with a simulation with all of the forcings in it. And here you might have the same period, sampled, subsampled in the same way. Observations are imperfect, of course. They don't have complete coverage over the surface of the Earth. And so you similarly, and in underdeveloped countries, for instance. And so what you would do is subsample the model, and in the same way as the observations have been actually sampled as well. And so what you have now is the capacity, with the full temporal history of the forcings driving this model, the capacity to do a back-to-back comparison with the observations. This is actually really challenging. This is really challenging because what it does is it reveals the differences in a very, very clear way. So we're all guilty of putting up a picture that goes, oh yeah, here's the observations, oh yeah, here's the model, oh they look the same, it must be true, right? We're trying to get away from that in thinking about detection and attribution. I'm guilty of doing exactly what I just described, by the way. Because there's more work in this, right? So that to say there's much more work in this. So what we do is we take the observation state, so it's a temporal and spatial time series. It's just a linear correlation. We've filtered it. We've got the model outputs. Now, in the case of current models, these are often the same variables. So it's temperature, surface temperature, surface temperature, so we're comparing the same units. Now, the model, actually, if you take not one model, but say 50 models, that's sort of what we have in the current assessment. You can have all 50 models in there, and of course, by averaging across models, you actually get rid of some of the structural errors that are in the models themselves, right? The multi-model mean is very often much more accurate than any individual model. But that difference leads to some model differences and model error. And then we have just simply a scaling parameter. In the simplest case of all forcings compared to observations, actually this scaling parameter is dimension 1. Right? It's just a scale. So if the model had a tendency to be underestimating the observations, when you solve this in a least square sense, what you might find is that the scaling parameter comes out at 2. What it's telling you is that it's trying to expand the model response to actually meet the observation. I was a bit surprised once to actually get the opposite, where instead of the model being more mute, it actually had larger amplitudes, and the scaling parameter might come out as a half, which is really telling you that the model is overestimating the response compared to the observations. Now you can actually solve this system, and the epsilon here is the observation error itself. So you can actually look at the residual with respect to the observation, so in effect from multi-model mean here, less the observations is the residual, and you can actually evaluate the goodness of fit, and you can actually test whether the models are formally inconsistent with the observations themselves under the hypothesis, in this case, that it's the all forcings example. And you can actually evaluate the amplitude and estimate the confidence interval on the scaling parameter beta. So that's the essential mechanism. So what is this doing? What it's doing is it's really formally making a comparison between the model fields, in this case, in this example, for all forcings, with actually all of the observations themselves. And so you can calculate out the 90%, 95% confidence interval on beta. You can actually test the epsilon against the a priori statistics, and you can then formally, with this approach, basically, and I've kind of gone through this slide in advance, and you can formally test that the observations really are reflecting, the model simulations really are reflecting the surface observations, and you can reject actually the model, or you can say that yes, you have detected a signal and the scalings are completely right. So that is really what we would do in the traditional total least squares approach, the optimal fingerprinting approach to assessing the surface observations, say, against the projections from the models. I will leave the presentation with you, Melissa, so that, of course, people can read the rest of this slide. But ultimately, what this really is we're really only looking for a very small set of beta values. Okay, so it's highly constrained, but it turns out to be pretty ill-posed because of the level of noise in the model simulations and the large internal variability, like the presence of PDO, SAM, ENSO, and so on. So those things, even though poorly represented in the models, lead to quite big contributions of error. And so there's a huge literature around actually solving this system in a way that regularizes and gives you the power to get a solution. Okay? So there's all the mathematics, which could be another couple of slides, but I've just skipped them out. But there's some just essential things to think about when you're thinking about detecting and attributing. So at the heart of this, really, actually, you need some signal, and you want a relatively small noise, right? So you want sufficient signal so that you can actually detect and separate. because of the way we set up the problem, typically, if you have a long observational record and you're testing things like solar variability or volcanic eruptions, you can actually make use of the temporal information to exclude the cause of volcanic eruptions and solar variability, because an 11-year cycle and episodic transient events are actually assessed in this process and can be separated out. It's key, actually, that you have a theory, you actually have models. Doing detection and attribution in working group 2 of IPCC usually involves ecosystems, things like that. Actually, you have very few models, very few numerical models for testing against ecosystems, sorts of... So really what that's telling you is we have a shortage of theory, right? So if there's no theory, you're in trouble. In climate science, we have plenty of theories. We've got a well-established set of equations. We've got a well-set of understanding, physical understanding. But actually in other fields, where you might want to detect and attribute human influence, we do not have appropriate theories. So even there, you can run into trouble. But in our case, we've got lots of long control model simulations, which allow us to understand internal variability. We've got ensembles to actually reduce the structural error that comes from the difference between models. And we've got various experiments for different simulations. And actually the CMIP-6 and the CMIP-5 protocols have particular experiments designed around actually understanding and attributing climate change. So we have typically the right experiments being undertaken, more or less the right experiments being undertaken for us. And then a key element is actually, do we get a consistent response? So I talked about the beta values being bigger than 1 or smaller than 1. And a completely inconsistent response would be if you've got a value of, I don't know, I'll show you an example where we get a value of 5, but where you get a too big a value or too small, what it's really telling you is the forcing isn't able to give the right scale of response in the observation. So it's important to be able to get a consistent signal. Because of the temporal information, often actually you can separate the signals between the different forcings, and I'll illustrate that in a moment. And in this case, really, the entire question around the total least squares approach, the optimal fingerprinting, is really trying to get statistical power on the solution, even though it's still poorly posed. So when do we have the most confidence? And I'll talk about some examples where we have relatively low confidence. We actually have the most confidence when we can separate out the contributions. So in some sense that they're not exactly aligned, right? But they're not exactly, nothing's ever orthogonal, right? That would be the best separating thing. But actually mostly they're a bit kind of aligned, but they're enough different to actually separate them out. Sometimes you can't separate them out. So you get the most confidence when you can do that, and take the different drivers separately and individually and sum them up. We've still got to account for the sources of uncertainty, so we've talked a little bit about that with models, model ensembles, model averaging, but there's actually sources of uncertainty in data. One of the things that comes really clear in IPCC is that we all have these time series. Famous scientists, not me, obviously, but famous scientists, they actually have these curves and they have these error bars on them like this. And the next famous scientist comes along and he has these small error bars. But actually the two curves are completely different and they don't overlap by the error bars. And then you get the third one come along and then the fourth one, and they're all different, right? So actually we typically do underestimate our systematic biases between our collections, and we don't actually get them to overlap. IPCC spends hours trying to get these collections to actually overlap, and it reflects the fact that there are systematic problems in the collections typically, and in the way that these famous scientists actually analyse their collections. So ensembles are really important for understanding those systematic differences in data collections. And the same is true of the models, and that's why we have the model ensembles. Now, there's this wonderful movie. Miles Allen is a hero. There's a few other heroes in the detection and attribution space, but Miles Allen is one of those heroes. And in fact, there's this very nice little link that's in the presentation, and he will explain to you in beautiful English accent, right? English accent. So I recommend that. I'm going to skip it, and we're going to move here. So one of the things that we're confronted by is actually at the global scale, can we attribute human influence to the observed changes? So this is the most simple graph that we've got, right? Remember, we're trying to communicate to policymakers, right? You know, IPCC is about communicating to policymakers. So this is a very large-scale summary plot that appears in the last IPCC report. And what it's showing you is that here are the observed changes since the 1950s, maybe 60s. 0.6 degrees of temperature change, and here's what the observed error bar says. This is an error bar that's actually got out of the many different products from the many different famous scientists. Here's the contribution from greenhouse gases. Now remember, greenhouse gases contribute positively to the temperature changes, and here are the contributions from aerosols. And you can see that the aerosol contribution is actually negative. The greenhouse gas contribution is positive. And the thing that's very tricky, now if you go through the formal detection and attribution process that I've just described, where you take both the count, the pattern and spatial information, what you rapidly realise is that the contributions from all of the greenhouse gases are relatively coupled to the anthropogenic sources, aerosols, particularly in the northern hemisphere, and because of the rapid transport of these things in the atmosphere, they tend to look like the negative of some of the greenhouse gases. And so what we have is the dilemma here that the greenhouse gases are producing something like 0.8, 0.9 of a degree of temperature change, and we've got a cooling from the anthropogenic, all of the anthropogenic sources, of about 0.3. So the combination of these two, of course, gives us what looks like the observations. That's the detection and attribution process. But you can see, actually, that there's a lot of uncertainty here. And if you think back about 5 slides ago, which I know you remember in detail, the error bar here is actually really small, but the uncertainty around the aerosols is really large. And what you can see is that the knowledge around greenhouse gas is actually really good. But the dilemma that we have is that the knowledge around the indirect and direct effects of aerosols is actually really poor. And so when you want to separate these two effects out, the errors tend to propagate and create uncertainty in our understanding around the radiative properties of greenhouse gases. So this is an example where actually a lot of the discussion around the uncertainty in greenhouse gases is actually a bit misplaced. Actually, it's to do with the fact that we've inadvertently done this complicated experiment where we've been doing two things at once. We're both modifying the atmosphere with aerosols and also changing the greenhouse contributions. And that uncertainty in the aerosols drives this uncertainty in the greenhouse gases. You can actually look at the all forcings, which is what this one is, all the anthropogenic combinations, and you can see suddenly the things that humans have influence over, aerosols and greenhouse gases, it actually collapses the error bar down much more. And then remember there were the competing hypotheses. Okay, natural variability. So is that a contribution to the observed changes? Here's the answer over the 50 years. Zero, actually. This error bar here. Oh, sorry, I beg your pardon. Internal variability is what is 0 with the error bars here. Natural variability here is actually contributions from solar plus volcanic eruptions. And you can see over the 50-year time frame of this detection and attribution experiment that actually it has nothing to contribute. So the really important, and in my mind, powerful thing about this figure, even though it's a summary, is what it's showing you is that, yes, we can account for the observed temperature change in a very formal way, very credible way, understanding all of the uncertainties. Yes, it is mostly driven by greenhouse gases. In fact, actually, you get way bigger response. So if we cleaned up the atmosphere, right, these aerosols typically lead to asthma and health effects, and estimated at $3 trillion globally. If we cleaned up the atmosphere, we'd actually see a bigger temperature response. But the combination of them can resolve very well, and that does offer a correct explanation. And all the competing hypotheses that come from other people, ones around solar radiation, internal variability, on this long time scale, are zero and have nothing to contribute. And so actually, if you look at this graph for a little bit, you'll realise that actually human influence are these two things, or the combination of them. And in fact, I think all of the observed changes can basically be accounted by human activity, and none of it by all the competing other hypotheses, right? That's the important bit. The competing things we know about, none of it is actually explained by. So the best estimate, so this is a direct quote out of the last report, best estimate of human-induced contribution to warming is similar to observed warming over this period. It's a bit namby-pamby. All of it's caused by humans, right? We can kind of look at it a different way, and this is a classic kind of approach. Here are the observations. So this is not going through the formal text and attribution, but it's intimately related. Here's the global average surface temperature and observations. If you just look at natural coursings, this is actually the trajectory that the Earth would have taken. So what it really means is the high incidence of volcanic eruptions and the various phases of solar variability would actually have a negative temperature trend since the 1960s. Okay? And you can see actually for the first half of the century, yeah, internal variability might explain the observations. Okay? In the second half, but if you add in the greenhouse gases, as we understand them, plus the anthropogenic forcings, what you can see is the two together, natural and anthropogenic, does explain the variations in global average temperature since the 1960s. And so that's a nice separation here. So this is where the signal to noise becomes really important, right? You can see that the competing hypotheses around natural variability has this level of noise. If you add in the greenhouse gas that's got this sort of level of variability, actually they separate out really nicely in the 1980s. And in the 1980s, we were just starting to do the first assessments, and that's actually where we started to say things like humans were having some effect on the climate system. In the oceans, we have a similar dilemma as we do in the surface temperature, and this is an example of just showing actually the improvement in the observations, which is shown by the black line here. And the reason we could see that the black in the fourth assessment, there's a bit of history here. Now, who are observationalists? There's no observationalists. There's 2, 3, 4, 5. It's okay. You can be an observationalist. I spent all my life being an observationalist. And who are modelers? Everybody. Okay. So, I'm digressing, but my observational friends say you can always simulate something. Observations are driven by theory. Okay. And that sounds like an observationalist speaking, right? Models and simulations are always driven by theory. So in the fourth assessment report, we had this lovely warm period in the 1970s in the oceans. And it was a bump like that in the curve. And the modelers, so most of you guys in the room, came along and you simulated the climate system, and it was sort of flat. And the observationalists stared at this for a long time and said, no, the models are just wrong. You guys don't know what you're doing. And it turned out, actually, so this is a case where the modelers and the simulators actually were right. They were guiding the observations and were querying the observations. It turned out that the observations had a time-varying systematic bias because the typical instrument record, which was from a falling instrument in the oceans down to 700 metres, had the wrong fall rate, right? And so it actually recorded things as being a little bit shallower than they ought to have been, therefore a little bit deeper than they ought to have been, and therefore it appeared as a warm anomaly in the 1970s. They got the fall equation better later on, and actually it closed down. They changed the instrument type, and it closed down the errors again. And so the important message was, because it equivocated, this difference between what the models were telling us and what the observations were telling us equivocated our capacity to be really assertive on the question that the oceans had warmed up. Right? It was actually undermining the science of climate change. It turned out that actually these errors in the observation record were corrected. So the observationalists were actually guided in this case by the modelers, by you guys in this room. And we corrected the record, and we got greater confidence because El Chichon and Pinatubo started to appear in the time series of ocean temperature, ocean heat content when you did a global average. Right? So that's telling you that we've got more confidence that we can actually see these very sharp, short, eruptive events that have occurred in the historical record. And so that gave us a lot of more confidence in the ocean temperature data. And then when you have a system that allows you to actually measure the energy balance in the Earth, you can actually do really interesting things like work out, well, how good does the observation system have to be to detect human influence? And this is what Peter Gleckler and Ben Santa did in 2011 or 12. They took all of the observation data sets, because there's quite a few. They included volcanic models with volcanic and all forcings. And what you find is that if you take the climate change models from a subset of what was available, you see they're all steadily declining with increasing greenhouse gases. That's the squiggles shown in the red. Okay, so I've kind of given you a couple of examples of detection and attribution where actually it makes sense to apply the method. Now I'm going to show you an example where in fact, in some ways, you can still get results out of it, but it ought not to be it's not the type of problem that's very super suitable for detection and attribution. But it was a critical issue in the fifth assessment report, and it's the story around the expanding sea ice in Antarctica, right? The expanding, all the climate projections of sea ice around Antarctica should say that actually sea ice should decline on total extent and area. And at that time, when we were doing the assessment, so that's back in 2012, we were confronted with this problem here. So the Arctic had a lot of attention on it, and you can see here the Arctic is declining beautifully. The red is the climate projections. The grey squiggles behind are actually the control model simulations. And what you can see is that in amongst these simulated planets, called Earth in this case, but in the virtual world, that the rising greenhouse gases led to a decline in the sea ice extent in September, so the winter at the time, sea ice extent in the northern hemisphere, which is pretty much in accord with the observations. And so you would say, oh, that's a completely satisfactory solution, and that's actually a problem that's very, very sympathetic to a detection and attribution approach. It's still got a lot of noise in it, but actually this trend, the underlying trend, is going the right way. But in the case of the Antarctic, here you can see there's actually a kind of a less noisy signal. All the climate projections have a weak downward trend due to rising greenhouse gases and ozone, which is also a competing hypothesis here in this in the question around the Antarctic. But the observations themselves were actually increasing at a kind of 1% per decade, if I remember correctly. over that period of time. So we were confronted with the fact, but the interesting thing is there's a lot of competing hypotheses here. There was papers around adding fresh water to the surface of the Southern Ocean, thereby causing a change in the stratification, thereby allowing sea ice to spread more widely. And there were multiple papers on that topic, and they had contradictory conclusions. So we were in the place where we have this really appalling sentence here. Just take your time to read it. We've got low confidence in the scientific understanding of the observed increase in Antarctic sea ice extent. That's low confidence. We don't understand the problem. Right? It's not the sort of thing you like to say, and it's incomplete, competing scientific explanations. So we're not sure what the hypothesis is to really test, right? And we actually had low confidence in the internal variability because, in some ways, the internal variability in here is actually bigger than the sort of internal variability we're observing. So at the time, the lazy conclusion, right, would be that, climate change doesn't have a strong signal in the Southern Ocean. It's not really any different from the control, so they're all the same. And really, it's almost in the envelope anyway, and so maybe it's no change and it's not important. Right, that's a lazy conclusion. Very easy to have concluded that. And we kind of did. So we did a little bit of work with Will Hobbs, and and we're trying to exploit and make use of the fact that there are different areas of the Southern Ocean which had different patterns. So this trend in the increase is sort of consistent with the deepening of a trough here, increased winds pushing the sea ice out, increased winds pushing the sea ice against the continent here. You see a reduction, you see an expansion. Can we make use of that in that signal, right? So that spatial structure that's in the observations by dividing it up into 1, 2, 3, 4, 5 areas, and see if we can kind of understand a little bit more about what's going on here. Now remember, it's bound to be unsatisfactory at one level, right? Because climate change will say that average trend's got to be going down. And so we went away and did this. So we'll look very carefully at all of the control simulations. And you can see the control simulations show this nice envelope here. Now this is for the King, Huckinen, Fifth area. Here are the observations, and here's where the climate simulations are going. So the climate simulations sit on the left-hand side of the control simulations. The observations sit on the right-hand side. So they've got diverging in opposite directions, okay? And similarly for all of the regions except for this one, they basically simulations sit on one side and the observations sit on the other side. But if you stare at this for long enough, right, what is the question we're trying to solve? The question we're trying to solve is, can we get any insight into why the sea ice is expanding? And we want to get rid of the lazy people who just think it's all sitting in the noise, right? The lazy people. So is it sitting in the noise? Well, actually, if you do the statistical analysis, the observations are statistically, that's what the envelope here is about, is statistically different from actually the control simulations. And yes, actually it's a real signal. That increase is a real signal, even in the case of our understanding of the observations. And relative to the control, actually the decrease is a real signal too. So if you think about it, what you come to the conclusion is that actually if we can kind of increase the statistical power, yes, that increases that we're observing in the field is a detectable signal in the sense that it's distinctly different from what the control simulations tell us. The historical simulations are also a detectable signal in the other direction. And what you're able to conclude, and that's the most important part, is that in spite of having an inconsistent problem, what we really conclude is actually the science is incomplete, right? So that's the important point. It's a very small step, but the important point is that the inconsistencies between the models tells us that the science is incomplete. We've got to look at the processes and add processes that are not in the simulations. I'm not going to talk about heat waves. So actually, so the things that changed. So the fourth assessment was in 2007. Okay, so in a period of 7 years, we've gone from saying almost nothing around some things to now actually having more confidence. Actually, the record's got longer. Actually, a lot of our confidence is because we've got another 7 years of recording. We've got a lot more confidence because we've fixed the errors in the ocean warming. We've got salinity telling us, along with the other measurements, that there's a change in the water cycle. I didn't talk about snow and ice, but they actually have similar detectable anthropogenic changes. Sea level rise I haven't talked about. It actually, maybe John Church talked about detecting and attributing some of the sea level rise to human influence. We've got information around temperature extremes and actually changing oxygen concentrations in the oceans, which I skipped over. And we produced a table actually in the fourth assessment. It has about 70 rows in it of parts of the climate system that actually got detectable and attributable contributions from human influence in it. And this figure is covering all sorts of climate indices. And this figure is kind of summarising that up. So what you see here is kind of a map of the world, and what you can see here is that we've gone to smaller regions rather than just simply the global patterns. And you can see Antarctica down here. The white boxes are the oceans, so this is the heat content changes in the oceans. This is over the land surfaces shown by the yellows, and the Antarctic sea ice, the Arctic sea ice. And if you stare at this picture for long enough, and it takes a while, I'm afraid, but if you keep staring at each of the panels in those pictures, what you rapidly realise is that the natural forcings is not sufficient to explain the observed changes up to 2010. And you can see that there's a nice separation of the all forcings, so natural and anthropogenic, from the natural forces. And it's emerging on every continent except Antarctica. I'll talk about that in a moment. And it's emerging in the oceans. Remember, the oceans are 90% of the global energy balance. And so if you take that plus the table that's in the back, really not only is the state of the climate system changed, but actually human influence is clear on all of the kinds of metrics that you might have about the climate system. So, I've just, I have a particular interest in Antarctica, right? But so if you read these chapters and you stare at them for long enough, you'll actually realise that where are the opportunities for new science? You guys are all good scientists, right? You're always looking for a new opportunity. Well, you can read one of these, actually. I suggest you read it, because actually you can harvest a bit of quotable quotes, as I've got here. Okay, sea ice extent. Shortness of the observed record differences preclude an assessment. Okay, there's a big red flag telling you to do some science around sea ice extent. There's and here's another quotable quote. Ice sheets, actually. I haven't said anything about ice sheets, and yet they're a huge contributor to sea level, and huge to the future projection of the sea level going beyond 2300. Yet low level of scientific understanding, low confidence in attributing the causes of the observed loss of mass in the Antarctic ice sheet. Another big topic for analysis. Here's a weird one, actually, because temperature, the most obvious variable we have, over every continent, except Antarctica, right? And anthropogenic influence has made a substantial difference. So Antarctica is kind of a bit of a hole. In fact, it was full of contrary problems in terms of, and similarly this one around, So Antarctica is ripe for scientific discovery. And actually, if you read out the other chapters, you'll figure out actually where the areas we should be working in. And have we actually improved, right? has science progressed? Why do we, and this touches on what I'll talk about in the next talk. So actually back in 1995, remember 1995? Margaret Thatcher and Ronald Reagan were, maybe they've just left actually, they've been pushed out of office. But, you know, balance of evidence, discernible human influence on global climate. It's a bit namby-pamby, isn't it? It's just kind of sort of saying there's some human influence there. In the third assessment, 2001, so most of us can remember that. New and stronger evidence, most of the warming observed in the last 50 years is attributable to human activity. Most of it, stronger evidence. Very likely, so there's a calibrated statement. Most of the observed increase in the global average temperature since the 20th century, very likely due to the observed increase in anthropogenic greenhouse gas concentrations. That's the fourth assessment. Very likely, 90% sure. That's what very likely means, 90% sure. Discernible influences to continental average temperatures, temperature extremes, wind patterns. Actually, if you look at the work of David Parolli and his cohort of students, there's a huge amount of information around extremes that's now available, even since AR4 and AR5. But I like this. Human influence, extremely likely that human influence is the dominant cause. Don't you love that? Dominant cause and extremely likely. What probability do you think that is? 99. Fantastic, isn't it? We're only 5% unsure. And human influence is more than double the probability of occurrence of heat waves. And even since then, we've had lovely results around that. And so what you can see actually in this history of headlines is this strengthening of the view around climate science. And so whilst you might think that you're not making much progress, actually over the 20 years we've made enormous progress in building the discussion and the evidence for human influence in the climate system. So that's the end of the first part. We'll take some questions and then we can move on. You're all worn out. Don't be bashful.
So we're going to be increasing the North Atlantic, and that,
yes.
How does that fit with a weakening of the AMOC?
Oh, that's okay. Completely okay. The North Atlantic is such a warm ocean that the equation of state allows you to increase the salinity in a huge way without really affecting the overall density structure. And so the weakening of the overturning circulation is almost unimpacted in that case by those salinity changes.
There's already so much salinity there.
No, it's just because most of the North Atlantic, where those temperature changes are, the contribution of density change is actually small. Is actually small relative to the warming and other things. Alrighty, well maybe we'll move on, but I have to find the talk. Yeah, sorry. Saurabh.
How much we are confident to assess the decadal to multi-decadal variability?
Say that again.
How much we are confident to assess the decadal to multi-decadal variability?
Yeah, so that's the noise in this discussion. With the long 50-year trends. So if we had more confidence on the decadal variability, if we understood more clearly, and the model simulated ENSO and we were able to phase ENSO up with the observation and Pacific decadal oscillation, we would actually reduce the signal to noise ratio, and actually our power to detect the slow human influence would go right up. So one of the things, so the hiatus is a classic example of a problem that we had in the last round of IPCC. Everyone's heard of the hiatus, I guess, right? Yeah, so the hiatus was a perfect weapon for anyone who wanted to talk about, and I hope Matt talks about this communication question. Perfect weapon for anyone who wanted to say, well, actually, the Earth's not warming up, right? And really, what was that? That was a particular phase of the Pacific decadal oscillation, altering the distribution of heat content in the altering the surface temperature in particular in the Pacific in such a way as that it looked like that the global average temperature was only going up slowly. It was still going up, by the way. And that was enough to allow people to raise scepticism. And we were unable to answer the question, right, as a scientific community. And as a consequence, much too much was made of the hiatus and of that decadal variability. Whereas if we were in a position to actually know exactly what was going on with the Pacific decadal oscillation, IPO, we would have actually put those natural variations correctly into context, and we would have had a story that would have navigated most of that problem that the hiatus language actually created. So decadal variability, and so all the key things, and if we could do a better job of those, would actually be detecting that human influence much more strongly, and in shorter timescales, actually, which is where we need to go. Yes?
We heard in a different lecture a couple of the ways in which we think the melting of Antarctic ice sheets are driven by the rotating continental.
Yep.
So what's still the main uncertainty that we have?
Well, just think about what you just said. So yes, most of Antarctica's mass loss is from beneath the ice sheet. That's fine. But actually, why is that melt accelerated on Antarctica? So why is the pathway of the warm waters able to cross the continental shelf? Wilma over there can tell you some of that story, so that's one of the barriers. But why is there more of that warm water moved towards the shelf, say? Okay, well, is it because we've warmed up the Southern Ocean, or is it because actually we've increased the strength of SAM, and so the westerlies have increased, and those westerlies have just sort of slightly reoriented part of the ACC, and so now we have a greater mass flux of warm waters. So the question of human influence is more complicated because you've got to drive the pathway between rising greenhouse gases to actually cause an increasing of the westerlies, which is actually driving that increased amount of warm melt that through various processes has actually crossed the continental shelf and allowed the cavities to be now warmed more often. And so the technical issue is not actually getting water across the continental shelf, it's actually establishing that the westerly winds were driven by human influence. Curiously, that's actually a bit open, and we don't even conclude that the westerly winds were driven by human influence in the last round, right? So it's unknown. It's another reason for reading the chapter, because you figure out the things that are missing, right? So that's what you have to prove to get the warming of Antarctica driven, right? And then you've got to be sure that the error bar that we have, and there's a lot of differences between the different products, is small enough that that's an incontrovertible thing that you can drive. And then the spatial pattern is correct around Antarctica. The spatial pattern is correct. That's another story.